All right, so our free response. Number one, the figure to the right is a snapshot of a wave at a given time. The frequency of the wave is 50 hertz, so they're giving us the frequency. The wave is traveling horizontally. And the first question says, what is the amplitude? Well, the amplitude is the maximum displacement of the wave particles. So the maximum displacement would be this. So if this is 5 meters, the maximum displacement would be up to the top, and it would be 10 meters. How did we get that? We got that by inspection of the graph. What is the wavelength? So the wavelength is, if we start at one point until it gets back to that same point again, that would be a wavelength. So we can see it's at the same point now, but it's headed in the downward direction. It starts out here going upward. At this point, it's going downward. So that's not one wavelength. Once it gets back to the same position and it's going up again, that's a wavelength. So rather than pick that point, that's a little confusing, why don't we pick the point at 0, if we can. And when it gets back to that point again, it's going down. Here, it's going up. And this is when it's at that point going down. So that distance from 0 to 4 would be 4 meters. So wavelength, lambda, equals 4 meters. What's the wave speed? They want to know velocity. And velocity equals lambda f. Well, we know lambda, we just figured out in part B, is 4 meters. And the frequency, they gave us 50. So 4 times 50 is 200 meters per second. Number 2, what is the period? What is the period of a wave with a frequency of 800 hertz? So we know period is equal to 1 over frequency. And the frequency they gave us was 800. So 1 divided by 800 is going to be 0.00125, and the units are seconds. Number 3, what is the wave speed if a wave has a frequency of 25 hertz and a wavelength of 5 meters? So velocity equals lambda f. The wavelength, they said, was 5 meters, and its frequency, they said, was 25. So its velocity would be 5 times 25, which is 125 meters per second. Number 4, what's the frequency of a 100-meter wave traveling at 2,500 meters per second? So we can use velocity equals lambda f. And we're solving for frequency, so we divide both sides by lambda, and we have frequency equals velocity divided by lambda. Our velocity is 2,500 meters per second, and our wavelength is 100. We can cancel out some zeros, so it looks like it's going to be 25 divided by 1, which is 25. Hertz is the unit. Number 5, if a guitar string has a fundamental frequency, so fundamental frequency equals 500 hertz. And they want to know the next 3 higher frequencies. So they want to know F2, F2, F3, and F4. Well, we can use the equation Fn equals n times F1. So the first fundamental is going to be 1 times 500, which is 500 hertz, which is what they told us. The second fundamental is going to be 2 times 500, which equals 1,000 hertz. The third is 3 times 500, which is 1,500 hertz. And the, this is the third one. And the fourth one is 4 times 500, which equals 2,000 hertz. So they're saying name the next 3 higher. So to do that, we want to say these are the next 3 higher ones. Number 6, a string with a length of 5 meters resonates in 5 loops. Here's the 5 loops. The string's linear density is 0.025 kilograms per meter. That's mu. And the suspended mass is 1 kilogram. What's the wavelength? Well, we can use wavelength equals 2L over N. They gave us the length. They said that was 5 meters. And now we have to count up how many humps there are, which is N, and we can see that there are 5. 5 over 5 cancels, so the wavelength here is 2 meters. Part B, what's the wave speed? Well, we can say velocity equals lambda f to get the speed, and we know the wavelength, but we don't know the frequency. So this isn't going to help us right now. We would have to look for another equation that can give us wave speed, and that would be velocity equals the square root of force tension over mu. Well, what's the force tension? If we look at the mass, its downward force would be its weight, mg, and the tension force is upward, right? So if we sum up the forces equals ma, and since this really isn't the mass isn't dropping or going up, it has no acceleration. Now let's sum up the forces. We have tension force going up minus its weight going down. So if we add mg to both sides, we see our tension force is equal to mg. So the tension force is mg over mu. Our mass they gave us was 1 kilogram, and g we know is 9.8, over the linear mass density, which is 0.025. And when we multiply and divide and take the square root, we're going to get a velocity for part B of 19.8 meters per second. Part C, what is the frequency of oscillations? So we have velocity equals lambda f, and we want frequency, so let's divide both sides by lambda. We have frequency equals velocity divided by lambda. We said the velocity was 19.8. Lambda is 2 meters. So for part C, we would get 9.9 hertz. Part D, what will happen to the number of loops? So the number of loops is n if the mass is increased. So if we increase the mass. So we need a relationship between mass, which is here, and the number of loops, which, well, the number of loops would be n, right? So let's say velocity equals the square root of tension force over linear mass. All right. Now we also know that velocity equals lambda f. We know that lambda equals 2L over n. So if we plug this in for lambda, we have velocity equals 2LF over n. So we have velocity equal to this and velocity equal to that. Let's set this equal to this. And let's do that up here. Square root of tension over linear mass density equals 2LF over n. So, going back to the question, if we increase the mass, which is in the tension force, we see that the n value is going to be inversely related, so it will be decreased.